What if I told you that making a light brighter doesn't actually make it more powerful? Not in the way you might think, anyway. Today, we are diving deep into one of the most important experiments in history, the photoelectric effect. It's a story about a single, baffling observation that didn't just break classical physics, it shattered it, and in the process, gave birth to the entire quantum world.
So, here's how we're going to crack this case. First, we'll look at what everyone thought should happen, the common sense prediction. Then, we'll see the baffling reality, where the experiments gave results that made absolutely no sense. After that, we'll see how a young Albert Einstein came up with a radical idea that explained everything. And finally, we'll explore the incredible legacy of that idea, which, believe me, is all around you right now.
All right, let's start with the common sense prediction. You see, back in the late 1800s, physicists felt pretty good about light. They understood it as a wave, just like a wave rolling across the ocean. A brighter light was just a bigger, more powerful wave. And the light's frequency? Well, that was just its color. So the picture was simple. You have an electron sitting in a piece of metal, kind of like a coconut in a tree, and you have this light wave gently pushing against it. Now, if you think of light as a wave, a couple of things should be true, right? It just makes sense. A brighter light, which is a bigger wave, should hit the electrons harder, knocking them out with more speed and more force. And a dimmer light, well, that's a weaker wave, so the electron might have to sit there for a while, soaking up energy, but eventually it should pop out too. Any light, no matter the color, should work. You just had to be patient.
And this is where common sense just flew right out the window. Section 2, the baffling reality. Because when scientists actually did the experiment, the results weren't just a little off. They were completely, fundamentally, and spectacularly wrong. The classical wave model failed in 3 critical ways. First, there was no time delay. Electrons were ejected instantly. The moment the light hit, they were out. Second, they discovered a bizarre threshold frequency. If your light's color was below this specific frequency, nothing happened. You could make the light incredibly bright, and still, not a single electron would budge. And third, the energy of the electrons, how fast they were moving, had nothing to do with brightness. It depended entirely on the light's color.
So let's tackle that first misconception right away, this idea that electrons need time to build up energy. I mean, classical physics wasn't just a little bit wrong on this one. The scale of how wrong it was is just mind-boggling. I mean, get this. According to the wave theory, for a really dim light, it should take an electron years, maybe even centuries, to absorb enough energy to escape. But in the lab, it was instantaneous. The very nanosecond the light turned on, electrons were flying out. This wasn't a measurement error. This was a sign that physics was fundamentally broken. And then there was that strange threshold frequency. The best way to think about it is like a password. Each metal has a specific password, which is a minimum frequency of light. If the light you're using has a frequency below that password, the door just won't open. It doesn't matter how bright the light is. It's like shouting the wrong password louder and louder. It just doesn't work. And that leads us to the second and maybe the biggest head-scratcher of them all. Everyone thought brighter light should mean more energetic electrons, but it didn't. What the experiments showed was that a brighter light knocked out more electrons, sure, but each one had the same maximum energy as before. It was like turning up the volume on a machine gun. You get more bullets, but they don't fly any faster. To make the electrons faster, you had to change the color of the light. Physics was in a state of total crisis. So, with physics in chaos, a young and relatively unknown patent clerk named Albert Einstein entered the scene. In 1905, he proposed an idea so radical, so completely out there, that it would change everything we thought we knew about light. What if, he said, light isn't a wave at all? He suggested that light actually travels in tiny individual packets of energy. Think of it less like an ocean wave and more like a stream of microscopic bullets. He called these packets quanta of light. We now call them photons. And this meant that the interaction wasn't a slow soaking of energy. It was a single instantaneous collision. One photon hits one electron. Boom. The absolute core of his idea is captured in this beautifully simple equation, E equals h nu. It says that the energy, E, of a single photon is determined by one thing and one thing only. Its frequency, nu, which is its color. The h is just a constant of nature. That's it. This is why a photon of blue light, which has a high frequency, is naturally more energetic than a photon of red light, which has a lower frequency. Its energy is baked right into its color. But how does a photon actually free an electron? Well, every electron is held inside the metal with a certain amount of energy. To get out, it has to pay what physicists call the work function. You can think of it as an escape fee. It's the minimum energy required for that electron to break free from the surface. So here is the new picture, and it's beautiful. A single photon comes in and hits a single electron. Instantly, it transfers all of its energy. Now, if that photon's energy is bigger than the escape fee, the electron uses part of that energy to pay the fee and break free. And what about the leftover energy? That becomes the electron's speed, its kinetic energy, sending it flying out of the metal. And this all gets wrapped up in one of the most important equations in physics, Einstein's photoelectric equation. The maximum kinetic energy of the electron is simply the energy of the photon that hit it, h nu, minus that escape fee, phi. This single equation explained everything perfectly. The instant effect, the threshold frequency, why energy depends on color, the entire mystery was solved.
Now, it was a beautiful theory, for sure, but science demands proof. So the question was, how could this be confirmed? And once it was, what did this new idea actually lead to? Let's dive into the quantum legacy of this experiment.
Well, the definitive proof came from an American physicist named Robert Millikan. And what's fascinating is that he initially thought Einstein's idea was reckless and set out to disprove it. He spent years meticulously measuring the energy of electrons for different colors of light. And when he plotted his data, electron energy on one axis, light frequency on the other, he got a perfect straight line. It was exactly what Einstein's equation predicted. He had accidentally proven Einstein was right. But the real insight here is even deeper. This wasn't just about light. The photoelectric effect was the first hard experimental proof that energy itself, at the most fundamental level, is not a smooth, continuous flow. It's chunky, it's quantized, it's exchanged in discrete little packets. You could almost say that the very fabric of our universe is pixelated. And if you're thinking, okay, that's a cool science fact, but why does it matter to me? Well, look around. This one principle, one photon kicks out one electron, is the foundation of so much of our modern world. It's how solar panels work. It's how the sensor in your digital camera works. It's even how the automatic doors at the store know you're walking up. All of it goes back to this one strange quantum effect. And that leaves us with a final, really fascinating question to ponder. If a simple experiment, something as basic as shining light on a piece of metal, was enough to completely rewrite reality, what other simple, everyday things that we take for granted might be holding the secret to the next great revolution in physics?